give a lecture and interact with us. That's an honor for us, I think. And I would like to ask Maharaj to give a speech for our seminar. Over to Maharaj, sir.
So most respected our Professor Arindam Ghosh, very senior professor of ISC Bangalore, and my dear colleagues of his department and my dear students, those are present in this platform and other YouTube and other platforms. So it is, I always have that and know that we are presenting today in this web platform due to this a good this, opportunity for us to witness a good lecture from Professor Ghosh. And all you have, I think, heard and all you have go through the media that Professor Ghosh, now it is he is a renowned scientist, especially in the physical science field. And this year 2020, he has got the prestigious Infosys award. And this Infosys award is really a very prestigious and very, I think, a commendable award in this sense that it is actually a pure gold medal, a citation, and 1 lakh USD dollar. And so you can brief tell the students especially that you understand the gravity of this award. And this work actually just according to the international research work, and those the awardee, they are actually just according to the international standard. So we are very, very happy that Professor Ghosh amidst us. From the very first beginning, on the outset, I extend on the behalf of all college and all the staff member and the students, Professor Ghosh, sir, we extend our heartiest congratulations to you for your commendable achievement, your actually tremendous sincerity, and all this dedication for this physical science research. I do not extend my talk. I welcome him on behalf of this college, on behalf of all our faculty members, on behalf of the students for this actually webinar. I tell the specialist student, you please actually enjoy his lecture, and after his talk, you actually interact with him. And his today's topic is very, very practical and very, very application based. So it is very interesting. After going through his title, I understand a very, very good topic he has choice for you. So all you enjoy his talk with this few words. I actually welcome him and welcome all the participants in this good webinar. Thank you, all of you.
Thank you, sir. Thank you, sir, for a welcome speech. And now I would like to ask Professor Ashok Pal to give introduction to our speaker. I know that he doesn't need any introduction, but still, from our side, as students should know who is our speaker today. So I would like to ask Professor Pal to give a brief introduction, and then she can hand over the platform to Professor Ghosh for the speech today. Thank you.
Okay. Good afternoon to everybody. I would ask every participant to keep their microphone off because substantial amount of feedback is coming. Participants, please mute your microphone. Okay. At the outset, I would like to express my deep gratitude to Professor Arindam Ghosh for taking time out from his busy schedule and being here among us to deliver a talk on a very modern, challenging topic entitled Emerging Physics and Devices with Atomic Membranes. At the same time, I heartily welcome Professor Ghosh on today's national webinar on condensed matter arranged by the Department of Physics of our college. To introduce Professor Arindam Ghosh, as I have collected from internet, in short, I would mention Professor Arindam is an Indian experimental condensed matter physicist, and at present he is a professor at the Department of Physics, Indian Institute of Science, Bangalore. PhD at the Indian Institute of Science on probing metal insulator transition and Coulomb interaction effect in doped semiconductor in 2000, following which he worked in Cambridge University, UK as a postdoctoral researcher. His current research interests include the transport properties of two-dimensional electronic system in semiconductors, carbon-based low-dimensional system, optoelectronic properties of atomically thin semiconductor membranes, magnetic nanostructure, and structural stability of nanoscale systems such as metallic nanolayers and nanoparticles. Professor Ghosh has published numerous papers in international journals and conferences, including Physical Review Letters and Nature Physics. As my earlier speaker has already mentioned, he has received numerous awards, amongst which I mention a few only. In 2006, he was awarded the UK India Education and Research Initiative Award. He was awarded the Shanti Swarup Bhatnagar Award for Science and Technology, the Prestigious Award in India for the year 2012 in Physical Science category. And in 2020, he was awarded the Infosys Prize for Physical Science, the most prestigious award that recognizes achievements in science and research in India. So, with this short introduction to our speaker, we all are eagerly waiting a question from Professor Ghosh, and so I would not like to lengthen the speech anymore and humbly request Professor Ghosh to start his talk. So, over to Professor Ghosh. Professor Ghosh, please.
Okay. Can you hear me? I somehow couldn't find the mute or unmute button. Can you hear me?
Yes, sir.
Yes. Yes.
Okay, good. Okay. First of all, thank you very much for a very kind introduction and your very kind words. Thank you very much. And I just wish to say that, everything that we do as researchers here in India is because of extremely high quality students that we get from all parts of India, particularly many. Actually, my first student was from Ramakrishna Mission, when I joined IIC as a faculty member nearly 15 years ago. And since then, we have been getting excellent students, and their training, their enthusiasm, their motivation have been exemplary. And without that, nothing would have been possible. Okay? So I think thank you for all, because all of you have contributed to everything that we achieve in our profession as a scientist in India. I'm going to talk about this very recent topic of 2D atomic membranes. I shall try to keep this as accessible to a broad audience as possible, but I would request you to ask questions anytime during my talk. I don't have to cover everything that I plan to, but at least I'll try to give you an introduction to a field which is rapidly emerging and expanding, and which will become technologically important as well as fundamental. Okay. So yeah, I mean, these atomic membranes are a type of new system. Well, it's not probably new anymore. It's at least 15 years old now, nearly. And a lot of people are working on this, but now only we are understanding the full gravity and its importance, how it can change our lives in the coming years. The difference between what is happening these days, let me just take you back, early 1800s, early 1900s or so, when Industrial Revolution came, what happened is that we started making machines, large machines, instrumentation, which revolutionized several sectors of textile, chemicals, and you could make nice large machines. And then when it came, you can get those machines led to high quality cars, and look what was there in 1911 and what we have today. So they all started with some form of revolution in instrumentation. That's what I would like to say. And it is the same instrumentation which with very high quality compressors, for example, which could compress liquid helium gas to liquid helium. And that led to discoveries, discoveries such as superconductivity. Nikola Tesla had the patent of creating the first compressor, which was later used in liquefying helium, and that paved way towards a large number of experiments in fundamental physics. But then it continued, the culture of instrumentation, and we could make the transmission electron microscope by the time 1931 came, and then scanning electron microscopes by von Ardenne in a few years later, which allowed us to see small distances, to look at small objects and create small objects, manipulate small objects in a way that could never be possible before that. So this history continued for further, and what happened is it started creating another direction where you start creating devices by using instruments, large instrumentation. And this devices led to semiconductor technology is today based on being able to create tiny semiconductor channels and billions of them, and gives you the computers that you have today, right? Synthesis of materials became an immediate beneficiary because very good quality instrumentation, you could create high vacuum chambers, for example, and those vacuum chambers could be used to create high quality material. And if you look at the high vacuum capabilities, 1960s saw the emergence of molecular beam epitaxy, with which you could create material of extremely high quality. You see, all your actually, I'll give you this example in the very next slide. Yeah, this one. You see the electrical mobility of electrons in high quality semiconductors became increased dramatically as you created better and better vacuum chambers, right? And you can see by 1980, and this is an old data, 1989, it increased by nearly 3 to 4 orders of magnitude, and now it's actually even 10 times larger than this. The electrical mobility is a benchmark of how good quality of semiconductors or material that you can create. Now, every time there is an improvement in a technology, there is an improvement in material property. And probably one of the very interesting examples is superconducting transition temperatures. You can see every time there is a high quality material that could be created, you can create a high quality, high efficiency capability instrument that is created. You create a high quality material, and that leads to new kind of material and superconductors, and you can see the superconducting transition temperatures are also as you create capability of instrumentation. What has been interesting to note is that by and large, the instrument and device developing setup have been independent of the material itself. So there's a symbiosis for sure of material synthesis capability and device technology, but they have been kind of moving relatively independent of each other. What I'm going to do today is to show that you are now going to create material of your choice and of your intent on a device directly. Okay, so material and devices are no longer an independent quantity, independent aspects anymore. And this is what these atomic membranes do in our technological development. Okay, so whole story started with graphite, and I'm quite sure many of you know how this story originated. You see, graphite is essentially a layered system in which billions of layers of graphene or single layer of hexagonal carbon atoms are stacked on each other. So this is an individual layer which is called graphene. And the interesting component of these material is that the layer interaction between two layers is extremely weak compared to other covalently bonded material or ionic bonded material. You can see the typical energy one is talking about between two layers is nearly 1,000 times smaller than that which is when you're talking about strong bonding between atoms and molecules in other kind of solids. Okay. And this was used in what you call exfoliation of these materials in to create or isolate a single layer of these two-dimensional solids. For example, the way it was done is that you take a bulk and you use a scotch tape, and it's very ingenious technique that was used nearly about a couple of decades ago, and using that you can create a single layer of graphene, which is one atomic layer of carbon atoms, and you can create you can stabilize them on a substrate. So what happens after that is people started making devices. Okay, so this is a picture of a graphene sitting on a silicon oxide. Let me just use my pointer so that I can. I'm hoping you can see my pointer now. Okay, so you can see a layer of graphene which is connected through some electrical contact by, so this is normally gold, and you can make what you call field effect transistors, in which the same field effect transistors which are used in computers and ICE integrated circuits, you can make the same thing using these atomically thin materials. And for that, there was Nobel Prize in 2010 to these two gentlemen. And then what we realize is that it is not just graphene, which is the material that can be created in a single atomic layer, but there is a large number of different materials which can be stabilized as individual atomic layers. These are some, for examples, graphene, of course, is what you know. These are all used or these are all created by a scotch tape exfoliation method or peeling. You just take a layer using a scotch tape and you press it on the bulk of this material, and when you take the scotch tape out, individual layers get stuck on the scotch tape, and you just press it on the substrate random shapes, but their thickness is really one or few atomic or molecular layers. You can see you can go from graphene, you can go to niobium selenide, molybdenum disulfide. This is a very important material. I'm going to come to that in a minute. And also the high DC superconductors, which are also layered systems. Now, before I go to those details, I'll just tell you the graphene is not really just a flat crystal. It's actually very, very interesting. If you take equivalent thickness of a graphene, it is actually 200 times harder than steel, except for the fact that graphene is extremely thin, but they're thick because it is sp2 hybridization between carbon atoms. Your material hardness, the material is extreme. Its elastic constants is much larger than standard three-dimensional material, okay? Or even steel, for that matter. And because it is completely transparent, it's 99.8% transparent, you can use it as completely different applications. For example, you can make windows in the solar cell, for example. A lot of people are trying to do this. There are technical challenges, but this is something which is also another direction where these kind of materials can be used. What we will be discussing primarily today is graphene as a field effect transistors, and you can actually use these to make extremely fast transistors. You see, one of the big problems of silicon-based transistors is that the mobility of electrons or holes in a silicon transistor is just about about 200 or something like that. So at room temperature, graphene can be much, much larger, thousands of times more than that. And as a result, you can make much faster electrical the field effect transistors up to a terahertz, which is simply not possible by using silicon-based technology. Interested to create such technological platform based on 2D systems, including graphene. Now, it turns out that after the discovery of graphene, somewhere around mid-2000, people have found a large number of them. Now, there are nearly 30 or 30-odd different materials for such layered family. Okay, you can see graphene is one, and there's a whole graphene class like boron nitride, graphene oxide, phosphorine, which is essentially the same with phosphorus. And then you have oxides, then you have chalcogenides. The dichalcogenides is very important because they are semiconductors. I'm going to come to that in a minute. You have got molybdenum disulfide. This is a structure, molybdenum disulfide, where you have a molybdenum layer which is coupled to 2 sulfur atoms on each side, and then they are essentially layered structures. Okay. Similarly, bismuth selenide, there is another class of materials altogether, but there is now nearly 35, 40 different classes of material that we know that we can simply exfoliate and stabilize on a substrate and then do very interesting fundamental experiments with it. What's interesting is that each and every of these materials come with very unique properties, okay? And extremely exciting to work in because the opportunities of making devices and fundamental discoveries become endless, and I'll show you how. For example, if you take graphene, and this is something which is very important component of graphene, why it was so interesting when it started, is because if I take graphene lattice structure, which is a hexagon, and you look at it in reciprocal space, it is also a hexagon. Okay, and this is kx and ky, and then what happens is that from this you create the energy bands of graphene, and the energy band of graphene is conical in shape. That means the energy momentum, kx and ky are the momentum in k space, and energy is in the y-axis. And you can see in energy is linearly proportional to the momentum. And the proportionality constant is with a velocity called Fermi velocity. And this is essentially like a photon. The photons, like light, has the same kind of energy dispersion relation, where the momentum is directly proportional to energy, and the proportionality constant is the velocity of light. In this case, the velocity is much smaller than light, but the electrons in graphene behave as if they're light, as if they're photons. Now, this is one type of two-dimensional structures like graphene. But the moment you go to other kind of two-dimensional layered materials like molybdenum disulfide, you can see here molybdenum disulfide is essentially a semiconductor, and it is in a single layer of molybdenum disulfide. You can see where my pointer is. The monolayer of molybdenum disulfide is a semiconductor with a band gap of approximately 1.9 electron volt, which is slightly larger, about a factor of 2 larger than silicon itself. Although silicon is an indirect band gap semiconductor, which is why, and molybdenum disulfide, if you go from 1 layer to 2 layers, 3 layers, and you make it thicker, its band gap actually becomes indirect. In a thicker molybdenum disulfide is an indirect band gap semiconductor, whereas direct band gap semiconductor becomes a single layer. When it's just one atomic layer or molecular layer, it becomes a direct band gap semiconductor. And this is similar for other family members of its family as well. But not only that, and this is even more interesting, that if you twist these molybdenum disulfide a little bit, okay, you can get from a semiconductor or a direct band gap semiconductor to a metal. For example, if you take a look at this structure, which is disulfide, you semiconductor. Okay, it's a 2H structure, the hexagonal structure. But if I shift one of the sulfur atoms by a shear force by about half a lattice constant, and it goes here, this is another structure called a tetragonal structure, a 1T structure, it becomes a metal. So you see the same system, the same material, you can go from a semiconductor to metal by simply twisting it slightly in its lattice structure. And this polymorphism is an extremely interesting and important resource with which you can make new devices that could not be possible with three-dimensional system ever before. And there are other phases also, which I'm not going to go into. A technologically important component is that these materials cover a very wide range of electromagnetic radiation because of their band properties. For example, molybdenum disulfide has a band gap of 1.9 electron volt. It absorbs very well in the visible domain. You can see here, this is roughly visible light energy is in the order of 2 electron volt. And I'm going to show you today, because this is one of my goals of showing the application of such abilities of these two-dimensional layers. So you see, the molybdenum disulfide can absorb light in 2 electron volt regime, which makes it immediately sensitive to visible light absorption. But if you go to other materials like phosphorine, like graphene, they can actually go to much longer wavelengths of microwaves, radio waves, which becomes strategically important in radars, in various other light detection. When you go to insulators like boron nitride, for example, it becomes important in the ultraviolet region because there the band gap is very large, and there in medical diagnostics and various other applications become very important. Now, if you think all these are the only thing, that's you are mistaken, because this is simply a tip in the iceberg. Okay, most of it. That there could be 1825 exfoliable material that we still haven't seen. We probably have seen just a tip of the iceberg, which is about 30-40 materials. But in principle, there could be much larger number of materials that can, used for their unique two-dimensional properties. And now, if I take one material of this, which is, say, for example, a transition metal dichalcogenide, like the molybdenum disulfide or tungsten diselenide and so on and so forth, you can see a same device can be used in electronics because it's a high mobility electron mobility transistor. You can make photo detection, that is detect light with it. You can use it as a solar cell. You can make it vibrate in a nano electromechanical devices. You can use it as a transistor, use it plasmonics, and so on and so forth. So what two-dimensional atomic materials have given us in the last decade or so is a possibility of using the same material backbone in a very wide class of applications, which is why it's such an interesting and important direction of research today. I'm just going to flash this because this is a very important component of today's lecture, that why there is a strong absorption of light by these class of materials called you see this transition metal dichalcogenide materials. Here, always remember this molybdenum, tungsten are transition metal, and sulfur, selenium, etc. are chalcogens. So that is why these materials are called transition metal dichalcogenides. You see, what is important here is that when at the energy scales of about 2 electron volt or so, where near the visible range, there is a very large density of states, okay, because of their unique electronic properties. And that's why it can absorb light extremely efficiently. So their ability to is atomic or molecular layer level is about 10% or 6 to 10%, which is unthinkable when you talk about three-dimensional material like silicon. So that is why these materials are extremely important when it comes to optoelectronic applications that I'm going to talk about today. However, before I say that, I'm going to tell you about what is happening today in terms of real research, that how are we making material on a chip. Remember, I told you when I started this talk, is that the concept of material design is changing slowly. And today, it is no longer material is being designed first, and then that is being applied in a device technology anymore. But now what is happening, they are getting merged, and we are making material on a chip. Chip and the material are looked at collectively. I'm going to skip this, and for this, all you need really, you can do it in your lab, in your college, and all you need is a microscope. And I'm just showing a microscope that I have in the lab, which is used to make these kind of materials. Here, this is a microscope objective. We create all our structures in this region, which is in the field of view, where we take material and put it on top of each other. And What I have shown you so far in this talk is how you use a single material, but what we do in the lab is what you call the van der Waals heterostructures, or what you call atomic Lego. In atomic Lego, you no longer look at one material anymore, but you start combining different materials one on top of the other. For example, I'm going to show you what you can achieve by making these completely artificial materials, where a material or multiple materials with different chemical origin of lead, each of them of course are lead, so that you can separate out their individual layers and put them on top of each other and create new structures. For example, if I go to this video, you can see if I take a layer of graphene and oops, sorry. That's it. So if I show you this, the layer of graphene is taken up, and then you put it on a layer of molybdenum disulfide, for example. This is the red one, is the layer of molybdenum disulfide, and you can make new kind of devices with it. If you want, you can make even more complicated ones. For example, I can make a 4-layer structure now. In the lab, this is interesting because you can make structures which doesn't exist in nature. You can take a layer of boron nitride, then you take another layer of graphene. This is a bilayer graphene, for example. And then you can take another layer of molybdenum disulfide and make a 4-layer structure. Okay? All these are actually very interesting structures because you have certain application in mind. Now, before I go, so what we do in the laboratory at ISC and many other places in the world now can be very nicely represented by structures like this. I'm quite sure, being from Kolkata, you all know what these kind of structures represent. This is a rocket shop kind of stuff, which is all created by Shukumar Rai a long time ago. And we are trying to do exactly this in the atomic domain, in which we are taking a material of different classes and putting them together and asking the question: are they useful or not? Or something like this: a giraffe and a grasshopper. Okay. So it turns out that this is possible. This is possible to put large number of these individual layers and create heterostructures. These are called van der Waals heterostructures because these are obtained from these van der Waals materials. When you call van der Waals materials, means that the materials which have got weak interaction between layers. Okay. This is how the real, for example, if you take a 5-layer structure, there are these two are essentially graphene layers. This is a 4-layer structure which is encapsulated between 2 layers of boron nitride. It turns out that this is an interesting structure because having boron nitride, which is an insulator, sandwich a layer of graphene can increase the mobility of graphene enormously, because boron nitride gives it a very high quality environment. Okay, you can do a lot of very interesting things, and people have now done very high electrical mobility. The same, it has now increased beyond orders of magnitude beyond silicon. You can make new kind of energy structures like a solar cell and so on and so forth. You can do different physics also, and I'm going to not go too much in detail. Quantum Hall effect, which requires high quality materials, you can investigate using these kind of new type of devices created by what you call this van der Waals heterostructure. What I'm going to do today, I'm going to give you examples of 2 directions in which we have been working on, and where you can use these van der Waals heterostructures. You can plan a structure so that it can serve a purpose. Okay? You design the property you want and create the structure on a chip, on a substrate. Okay. And this is, the first thing is the heterostructure of graphene and molybdenum disulfide, with which we do optoelectronics. Now, before I go into the detail, I would like you to get a little bit of a definition about what is optoelectronics, and in which optoelectronics is a field in which you convert electricity, you convert light. I'm going to talk about light being converted to electricity. And the better is the conversion, higher is the efficiency. And for example, a camera does exactly that. A camera is essentially a system in which light falls and then it gets converted into charge, and that charge gets stored, and a digital camera essentially creates an image out of that. Now, if you want a good quality camera, you want to create larger current for the same optical power so that you can image in the night and so on and so forth. Now, if you see the way this efficiency is designed or is defined, is photocurrent is the current that is generated when light falls on your camera or in your material. And P is the power of photoexcitation power. And these two are proportional to each other, and the proportionality constant is called responsivity or photoresponsivity. The photoresponsivity is a quantity which is given by this efficiency, quantum efficiency called eta, multiplied with the charge E, electronic charge, divided by h nu, where h nu is the energy of the photon that has come on it. Okay. Generally, if I put numbers here, it is in the order of 1, the intrinsic responsivity in the visible range of photon energy. And if you look at a typical quantum efficiency of 1, if I take, then in that case, the energy is, the responsivity is usually, or intrinsic responsivity is in the order of 1. Now, it is very poor in the case of graphene, because graphene cannot absorb light. Most of the graphene is nearly 98% transparent, which means most of the light goes right through graphene. Okay. And it doesn't absorb. Graphene is very poor, even though it has got a very high electrical mobility. It is a very poor converter of light into electricity, graphene alone. Okay. As a result, the photoresponsivity is extremely poor. This is in the order of 10 power of minus 6 rather than 1 that I showed you earlier. However, if you see, as I told you earlier, because of this density of states in this transition metal dichalcogenides, the light conversion efficiency into electricity is good in these kind of materials like molybdenum disulfide. But the problem is that they are not high quality electron mobility transistors. That means electrons do not go in these kind of systems very, very fast. They are usually standard semiconductors. So in one hand, you have got graphene, which doesn't absorb light, but there the electrons can move very fast, very efficiently. On the other hand, you have got this transition metal dichalcogenides, which can absorb light very well, but there the electrons cannot move as fast as they can move in graphene. So this is a very interesting scenario, and both are layered materials. So we thought long time ago that whether if you combine these two, whether you can come up with something, a new, completely new structure where you can exploit the best of both worlds. Okay, and we made this kind of device many years ago now, nearly six years ago, and showed that I'll just quickly show you how this looks. So okay, let me just. I'm sorry. So you can see this is a typical device structure in which you create this new material with graphene on top and molybdenum disulfide at the bottom. And the whole thing is usually put on a device of a transistor-like device, where the silicon oxide is the dielectric layer, and doped silicon is the metal gate, using which you can change the electrical carrier density of graphene. So if I apply a voltage on this doped silicon, I can make these graphene more, I can induce electrons or holes in graphene. Okay. So you can look at the molybdenum disulfide, it's the standard transistor. So you can see if I apply gate voltage, molybdenum disulfide increases with gate voltage because it's an N-type semiconductor. And if I now look at the voltage, the electrical conductance or current in the graphene, then it shows as I induce holes in it, the current goes up. As I induce electrons in it, the current goes up as well. So this is graphene's characteristics. This is in dark, without light. But if I shine light now, you can see something really interesting, that the current has changed in the graphene layer. And this current change is called the photocurrent, because this change in current comes because you have been shining light on graphene. Okay. And if I take this change in current, which is the photocurrent, and divide that by the power, And this is something which is very interesting. The power is this ratio is the responsivity. Instead of 1, which is the intrinsic responsivity, these kind of heterostructures, you can get nearly 10 to the power of 10 as ampere per watt, which is nearly 10 orders of magnitude larger than standard photoresponsivity in three-dimensional bulk systems. You can easily get similar enhancement in the room temperature as well. It is currently the most sensitive optoelectronic element available to human being. To give you an idea about how sensitive such kind of sensitivity, how this, what this sensitivity really means, 10 to the power of 9 ampere per watt, in a lab we can measure 1 nanoampere of current, which means I can actually determine nearly 10 to the power of minus 21 watt if I have a system of this sort. And that essentially means something like this. Suppose you have a candle. Okay, a candle emits approximately 18 milliwatt. That's why it's called a candle within a unit sphere around it. And if you have a candle in the on Earth, which is about 364,000 84,000 kilometers from the moon, and you create a 1 square meter of this material, and keep it about 1/3 the way to the moon, you should be able to detect a candle of which is lit on the Earth. So this is the kind of sensitivity we're talking about. Of course, there are other technological problems, but at least what I'm trying to give you is some form of an idea of how sensitive these kind of materials can be if you have, if you want to convert light into electricity. Using this, now we have been able to create single photon detectors. You can see the individually photons are created. Every time you shine a photon, 1 photon can lead to drops in the current. So you can use it in quantum technologies, which can be used in which uses the number, which looks at the number of photons in individual bunches of light, and you can create lots of very interesting applications. You can see if you can have a very weak light, most of the photons. This x-axis is the number of photons which is impinging or incident on this hybrid materials. You can see as you increase the photon flux, you can see from maximum number of 1 photon, you go to 2 photons, then you go to 3 photons, or towards that as you increase the number of photon flux. You see, the interesting part here is that you see these are all bunches of light, and photons are Poissonian distributed. That is, the probability of photons being emitted in a bunch is a Poisson distribution, and you can see that kind of Poisson distribution can be outlined with such detectors. Where all these are taking us to futuristic LEDs, for example, in which entire LED is tunable. You can change the same LED, can be changed, can be used to different colors. You can look at extremely miniaturized LEDs using different forms of light, different forms of two-dimensional materials, and so on and so forth. I don't understand how much more time do I have. I have. I'm hoping that I'm still online. So can you tell me whether I can have 10 more minutes?
Yeah.
Okay, good. So this is one of the sides of the applications. Now I'm going to give you a completely different application, which is again interesting because it's the same material backbone and going from optoelectronics to a different side, and that is another interesting material called neuromorphic computer design. You see, neuromorphic computing designs are extremely important. I do not know how much you are being taught this. Neuromorphic designs are those in which you look at the computational aspects of a computer, which is essentially a serial process. You have storage in one side and processing of information in the other side. And that can, this is what we call a von Neumann architecture of computing. But now what happens is people are looking at alternative computing architectures. And neuromorphic architecture is one of the more very important and interesting directions which can probably affect artificial intelligence designs, machine learning, and so on and so forth, where you deviate from the von Neumann architectures and you use materials or systems in which you do the processing of information and storage of information simultaneously. Okay? So it's the same material or same device which can store and process the information. Okay? So this is called neuromorphic computing design, and the perfect way looking at neuromorphic designs is how does brain work. So brain-inspired designs are one of the most common architectures of neuromorphic computing. So just to give you a rough idea about how this thing works, suppose you have got two neurons, and one of them is and they are connected through what you call synapse. Okay, and this one is called presynaptic neuron, and this is the postsynaptic neuron. Of course, there's a dendrites which are connecting them. So once you have that, then if you want information to flow from the presynaptic neuron to the postsynaptic neuron, then the synapse allows that, because that's a causal event. So for example, if this is going from, information is going from presynaptic to postsynaptic, because you want to have the cause precede the effect. You don't want the effect precede the cause. And when presynaptic neuron information goes from presynaptic to postsynaptic, you want those synapses to be effective or conductive. So you want a memory of some sort, which can, as you give pulses from presynaptic neuron, the conductivity should increase of the synapse regions, and this is called potentiation. Now, if the opposite happens, that means somehow, if the information ends up flowing from the postsynaptic to the presynaptic neuron, then you do not want that synapse to be effective, because that is a causal event, and you want to stop them, correct? So how you stop them is that you remove the conductivity of the synapse, and this is what is called a depression. So this is one of the models. There are many models in which the neuromorphic designs of memories can be designed, but this is one of the ways we have tried to understand how to design the brain. That means channels which naturally reinforce each other each time there is a causal event, and it naturally deactivates itself if there is a causal event. Okay? The potentiation means you increase the conductivity of the synapse. Depression means you decrease the conductivity of the synapse. Every time there is an acausal event, which is these red ones, which are opposite. I have drawn negatively because information is flowing from the postsynaptic neuron to presynaptic neuron. If you have too many of them, the synaptic conductance goes down. So, question that we have asked in our research for a while is that, can we create structures in which we can mimic this? That means we can mimic we can create memories with which we can either use continuous pulses can increase the conductivity, and continuous pulses of the other side of the negative origin can decrease conductivity. So this is essentially a memory, designing of memory. And I'll show you a design. It is very similar to what we have done in the case of optoelectronic systems. Again, you see, what is interesting is that we are going to use the same set of materials, which is 2D atomic layers, and make two completely different device structures. One is optoelectronics. We have used the ability of the chalcogenides, transition metal chalcogenides' ability to absorb light in making high absorbance photodetector. But now we are going to use its ability to act as an electrical transistor to make a new kind of memory. What you do is that you take the silicon oxide surface, and then you put a layer of graphene, something like this, and this is what will work out is as a gate, which is an intermediate gate which will store charge. And then you put a layer of boronite, right, which is an insulating two-dimensional layer, which is also a layered compound, as I told you earlier. And then you put a layer of molybdenum disulfide. Okay? And you can see the molybdenum disulfide layer is a semiconductor. As I told you right in the beginning, this semiconductor is like you can make a FET or field effect transistor from this semiconductor, and we have done it many, many times. And then what you do is that you put electrical contacts on this, and this is called a floating gate. This graphene underneath is called a floating gate. A floating gate simply means that it's a body that can store charge. Okay. And hence it can charge up to a potential. If you, like any conductor, if you apply charge, then its capacitance is C, it floats up to a voltage V. And if it floats up to a voltage V, it affects charge transport in this molybdenum disulfide layer, and hence you can control the charge transport in this layer by a potential that is being developed in the graphene layer. And then you apply electrical pulses. Now what we do here is simple. We essentially put in electrical pulses on this silicon gate, which is also a metal. And every time you put pulse on this, you can positive pulse. What happens? Charge flows out of the boron nitride, out of the molybdenum disulfide layer, and gets stored in the graphene layer, and that leads to a change in the conductivity of the molybdenum disulfide layer. And if you give an opposite pulse direction, then exactly opposite thing happens. That means charge goes out of the graphene layer and gets stored in the layer, which is which essentially makes the conductivity of the MOS2 layer opposite. So the goal here is to use this MOS2 as a synapse on the silicon gate, as if these presynaptic and postsynaptic signals. And what we're trying is that we are seeing that if I give you positive pulse, is it increasing the conductivity? And if I give negative pulse, is it decreasing the conductivity? And exactly that is what happens. And this is interesting, because what happens is that if you see that every time I give a positive pulse, the conductivity increases. This current ISD is the current through the MOS2 channel, which is a semiconducting channel. Every time I give a positive pulse, there are 12 pulses here. Every time I give a positive pulse, it goes up. And then I invert the pulses. This is the inversion of the pulse, and it's called a depression cycle. And you can see every time I give that, the conductivity goes down. And you can go on doing it. You can go on doing it millions of times, okay? Like the brain works. Okay. So what's interesting is that we have now been able to achieve a completely device at different functionality using this, and I'm able to create devices which mimics the activity of a synapse which connects to neurons. Okay? So it can be now used in some neuromorphic designs. But the question that you can ask is that, okay, is it useful? Why are you doing this? Going all sorts of device design which can mimic the functionality of the brain. And I'll give you the last piece of information. That is, look at the kind of energy scale that is involved in making such, synapses. You see, typically the energy dissipation, every time you give a pulse of voltage and current flows, then you dissipate energy. And the total energy you dissipate is essentially a product of voltage that you apply multiplied with the current that you have passed. And as you can see, the typical energy dissipation for every time I use this kind of power, picojoules to femtojoules. If you look at this last two columns, is essentially the comparison of energy dissipation with these kind of unique neuromorphic designs in comparison to other kind of existing neuromorphic designs within semiconducting platform. For example, silicon FinFETs are also used. Indium zinc oxide and zinc oxide, 2D materials have also been used for these purposes. And you can see the kind of energy scales involved in this kind of synaptic operations, which is in the orders of picojoule to 10s of picojoules, 45 picojoules, and so on and so forth. Whereas this one is actually enormously small, except for the fact that in PEO, this is the organic semiconductor, the kind of energy scales involved is in the orders of few attojoules to femtojoules. And if you ask the question of how much does the brain use for individual synaptic operations, it is in the order of few tens of femtojoules in magnitude, somewhere in the order of 10 power of -2, about 10 femtojoule or something like that. So you can see that these kind of new designs of neuromorphic platform is needed to make efficient neuromorphic architectures. Okay, so I'm kind of going to stop because what I'll do is that I'll take more questions as and when it comes. But before that, I want to give you an overview of what one could do with these. It's not only detection of photons, but it is also other kind of designs. And one of the things I did not talk about today is thermoelectricity. You can make unique thermoelectric designs as well of extremely high efficiency, and this is kind of underlines our work here. What we do is we design materials using two-dimensional layers, and we appropriately stack them on top of each other, and we kind of we ask the question, okay, what property of the two-dimensional materials that we are going to use to get a property that we want, device functionality that we want. As I showed you today, using the single photon, we can make single photon detectors or extremely high efficiency optoelectronic material by using the light absorbing property of chalcogenides. But at the same time, we can make interesting memories by looking at the transistor property or FET properties of the same two-dimensional materials. So essentially, it's an imagination that you would like to, look at and then stack the materials. I'm going to stop here and let's see if you have got questions. I'll be very happy to answer.
Thank you, Professor Ghosh, for wonderful talk. I would like to ask ADC sir if students have asked any questions to him also, means he can ask on behalf of them. Otherwise, students are invited to ask anything, means any questions so far connected to this talk.
Well, Kolon, actually, I have one question in the chat box from a student on his host. Can you hear me?
Yeah.
Hello?
You can.
Actually, a question. There's a question from Onimesh Hope. He asked the following question: I heard that if we put graphite dust on glued face of a sellotape and cover the dust with another sellotape and start to cover and uncover the sellotape few times, we can be able to get a graphene. It is true. Why it is so strong? This is the question.
Yes, it is true actually. So if you start essentially exfoliating graphite continuously using sellotapes, yes, eventually you will stand up. So eventually you will get a single layer of carbon atom. Actually, this is how originally it started, but this is something which is not used anymore. There are more refined techniques of exfoliating graphene. But yes, answer is correct. You can create graphene by simply taking a sellotape and keep on exfoliating it one by continuously. What you need to do after that is that you can press it on a substrate like a silicon oxide substrate, and then use a microscope. And that's what is extremely interesting, is that even if you have a microscope in the lab which is not very high quality, you should be able to see single layer graphene in your microscope.
Okay, and there is another question from Shayan Chatterjee. He's asking, are we looking for something which has both high electron mobility and high light absorbing power at the same time?
Eventually, answer is yes. It's a good question, but you see, the problem is that they do not come together in most materials, and this is where, as I was saying, the imagination of material design comes into play. And what I have tried to do today is to show why two-dimensional atomic membranes are so interesting. Because what you can do is that you can take a material which is of high electron mobility, and you can take a material which has got a band gap which can absorb light very well, and put them together to create something completely different and become an extremely interesting concept. You see, the problem is, if you same in the material, there is a problem, because the moment you have a band gap which is necessary to absorb light, you cannot get high electrical mobility in that, because the band gap it creates the disorder becomes very strong and it scatters electrons as it tries to go through. So getting extremely high quality material with a band gap, high electron mobility material with a band gap is challenging, which is almost physically impossible. Whereas vice versa. So if you want to remove the band gap, in which case the screening of the disorder is very good and you get high electrical mobility. But in that case, you do not get absorption of light. And this is what is interesting. The 2D atomic membranes give you the possibility of building a solid now. It's essentially a solid, right? Essentially in which individual atomic layers, which are separated by a van der Waals distance of 0.3 to 0.4 nanometer, which is essentially what a solid is made of. In a solid, mostly the atoms are separated by 0.2, 0.3 nanometer distance, 3 to 4 angstroms. You are essentially building that. You are building a new solid in which you are incorporating these functionalities, in which you create a, you create high electron mobility in one layer and light absorption ability in the other layer, and get both of them together in your functionality. So I'm hoping I tell you where the conceptual advance has been made.
Dan, I think you have got your answer. There is another question. No, I don't think. Kollan, do you have any question in the chat box?
I'm also seeing. Let me check. Someone.
Sir, let me ask you one question, sir. As you have mentioned in your talk that we can create heterostructures by stacking layers of different materials, sir, what is the guarantee that the resulting structure will be stable?
I'm also trying to get the answer. Since you just asked my question.
Okay, yeah, this is a very important question. Of course, first of all, the stability of such structures are certainly not guaranteed. There are only certain section of materials that we now know are stable on a substrate. You see, these are atomic layers, so their thickness is in the order of 0.5 nanometer, 5 angstroms or so. And so it turns out that in spite of their thinness, they are extremely stable. Okay? And for example, graphene, actually when graphene first came in 2004, 2005, there are a lot of fundamental issues that came out, that can a purely two-dimensional structure be structurally stable? Normally there is even theorem called Mermin-Wagner theorem, which says that such structures are intrinsically unstable. But it turns out that because of the substrate, probably, that interaction with the substrate can make such structures stable. Okay? But not all of them. For example, not only the structures can be unstable structurally, but they can also be extremely sensitive to environment, gas. For example, molybdenum telluride, which is a very interesting material because it has very small band gaps, so it can be used for microwave and infrared detection. The moment you take them out in environment, they become unusable. You have to create them in a completely inert atmosphere and make devices there. So there are obviously several factors which can affect stability, structural stability, which is why we now know just about 30 to 40, and people are working on it to see if there are other structures which are available. But yes, there are problems with structural stability, but there are 30 to 40 materials which we now know. They can be mechanically exfoliated and shown to be stable on a substrate. There are some of them which can be made at a large scale also. Graphene and molybdenum disulfide chalcogenides, they have been created in a large area, and they have been shown you can create them at a wafer scale if you want to create really a commercial device, and that has been shown to be possible.
Thank you, sir. There is another question by Anshuman Pathak, but I think that's a very fundamental question. What is a field effect transistor? Means I think you can you are talking about lots of FET, so I think he wants to know what is that.
Yeah.
I think
So field effect. So what's the question?
it's a why. What is a field FET?
Oh, acha.
I
Okay.
think
Good. No,
these
I
are
probably
fundamental
spent.
things.
Yeah, no,
Yeah.
that is it's a perfectly valid question, and I think I went through fairly quickly in that I showed I showed this in the beginning, but let me quickly tell you what a field effect transistor is. I'm just trying to see if I can. Let me just check if I think it will be difficult. So suppose I have this structure, and this is a what we call a channel. This graphene is a channel, and you have this gate. This is silicon plus plus is a metal. It's essentially a metal because you dope this very heavily and it becomes metal. And the silicon oxide is a dielectric. Okay, and what happens is that if you apply a voltage is essentially you apply an electric field. When you apply a voltage here, you apply an electric field between the graphene channel or graphene layer and the gate underneath. So this electric field creates charge in the graphene layer, and then the electrical current flows because you now have charge which allows electrical current to flow within this channel or within this layer. So this is a field effect transistor because you have applied a field to make current flow between in the layer. So this is a transistor operation and fundamental of transistor operation. Most of our 2D atomic membranes, the work started from the concept of field effect transistors. Is it okay? Or if you want, I can explain it in more detail.
Yeah. Anshuman, I think you got your answer.
Yes, sir.
Thank you. So, any other questions from other
There is a
students?
question, Kullan, from Devayun. He has
Okay,
asked
sir.
one, Devayun. The question is, will this heterostructure become the proper silicon as a semiconductor in future? As silicon is
Right. Right. So this is a hard question, but I have to say that, you see, one of the most important aspect why people are looking into. First of all, there are certain things you can do with these two-dimensional atomic layers that you simply cannot do with silicon. For example, flexibility. Two-dimensional layers are, because they are so thin, you can immediately bend them, fold them any way you want. If you put them on a flexible substrate, you have a transistor which is completely flexible. So if you want to look for flexible electronics, and where I don't think silicon is a solution. So in those kind of sectors, people are already trying to put in molybdenum disulfide because molybdenum disulfide is a semiconductor and atomically thin semiconductor, which is perfectly flexible. And that's one direction where obviously 2D atomic layers are already superior. Now, silicon industry is $1 trillion industry, $24 trillion. I mean, that's a huge number. You cannot replace silicon industry straight away. But what you can see that there is probably a bottleneck that is around the corner in terms of miniaturization. What is happening is that as you make the silicon devices smaller and smaller, you have, because of the thickness of the silicon, which is in the orders of 10 to 15 to 20 nanometers, thickness, not the length, you have several problems coming in terms of drain-induced barrier lowering and various other kind of channel effect, short channel effects, which makes the off state of a transistor is relatively higher in conductance. Current flows, even if you switch off your laptop, the current will still flow and keep it warm. So, and that happens when the silicon is, because silicon is after all a three-dimensional system. So what people would like to do now is thin down the channel width to as small as you can so that you can go to off state far more efficiently. And all these thickness-induced problems like the drain-induced barrier lowering and others are actually minimized. So what is happening is, and also use, get new architectures like tunnel field effect transistors and so on and so forth. So what is going to happen in probably a slightly longer time? The electronics with semiconductors or 2D semiconductors are going to take up some niche market, probably ultra low, say flexible electronic market. Then probably it's going to go towards low energy or energy efficient electronic market and so on and so forth. And then also because you have these materials which are available at the surface, you can use them for other applications like optoelectronic applications, like neuromorphic applications, which silicon will automatically be far more complicated in terms of structures. So I think it will happen in stage-by-stage manner that eventually probably we are looking at a different platform of electronics and other technological advances like the quantum technologies, for example, will probably be affected seriously by two-dimensional structures, far more than silicon appears to at this point. I don't know. Is that clear in the vision part?
Anyone else have any questions? Okay, so let me ask one question, sir. That we know that today the wearable materials which can actually monitor some of our health things, the heartbeat and all these things from a very low powered devices. And do you think this type of materials are going to enhance this type of electronic gadgets and all the wearable means suits and all these things in our near future?
I mean, there are some applications which are already coming in. There are composites which are created. Wearables is, there are two ways. For example, one is creating conducting polymer in which you put graphene and mix it with polymer and you get new type of graphene, new type of high strength polymers, which can be used not only in wearables but composites of various types in day-to-day activities and in utensils and so on and so forth. As far as the direct electronic application is concerned, it is still under study. And what needs to be done now, and this is what is happening, is creating 2D materials at the wafer scale. And there is a huge amount of work that is going on, because you see the wearables or any other application requires material production at commercial scale. Silicon is very important today because silicon can be created in very large quantities in very large wafers, and 2D material is just about a decade-old industry or system. And as a result, what people are now doing is making wafer scale growth of two-dimensional materials of atomic layers, which could be then used for large-scale device fabrication, and then naturally it will become a commercially viable alternative to silicon industry. So right now there are, as I said, there are two issues: putting these 2D materials in composites, which can make very good quality a different set of applications. And when it comes to flexible electronics, wearables, etc., for that wafer scale production of these materials are becoming more and more important. And once that technology is standardized, I think we will see wearables based on 2D materials fairly soon, I would say.
Thank you, sir. Thank you. Elisa, sir, any other questions from students?
No, there is no other question, I think, Kullan, in the chat box.
Okay, so if no other question, then I'd like to thank Professor Ghosh for giving an illuminating talk on such a nice subject. It is a very recent subject, and I think our students have been exposed to such a new subject, and that is very exciting that in new and near future they can also be a part of this research. So having said that, I would like to ask Atis Dipankar sir to please give a vote of thanks, and then we can come to an end.
Uh,
Thank you, sir.
Okay. A very good, a very good evening to all of you. Actually, now we have come to this, and prior to winding it up, I would like to propose the vote of thanks to all who have helped us in making this seminar such a success. First of all, I would like to propose to our speaker, Professor Arindam Ghosh of Indian Institute of Science, Bangalore, interesting and thought-provoking talk on graphene. Actually, he has introduced the topic graphene to our students. Thank you, sir, for this your thought-provoking presentation. I would also like to thank our principal for support and guidance, and finally the students who have turned up in such a great number, and not only from our department but also from other departments of the college, for your active participation in the seminar. And once again, I thank you all for your kind. Thank you.
Thank you. This was a pleasure.
Thank you, sir.
See, Professor Ghosh, when you come Kolkata, I in advance inviting you. Please visit our college and also department.
I will. Thank you very much for the invitation. Yeah, every time I go to Calcutta, I try to visit, but we have not been traveling too much because of all the pandemic. But I mean, when I come to Calcutta, it will be very. I have been in St. Xavier's College, and of course there are various for all my childhood.
Yes.
So yeah, so I will be very happy to visit.
Yes, sir. Please do.
Yes,
And visit
I
our
contact with
students.
you when you come.
Yeah.
Please give me a mail so that I contact personally and actually invite you to my college and our department also.
Certainly. Thank you. I will be very happy to.
Thanks again for a wonderful talk, sir. And
Thank you.
wish you
Okay.
seeing soon.
Thank you.
Thank you. Let us call it a day, friends. Okay.
Bye-bye.
Here we stop the seminar. Thank you. Thanks everyone for joining and making it happen. Thank you.